We measure voltage using a voltmeter, and this time, although an ammeter is set in a circuit, as part of the circuit, you create a gap and put it in, a voltmeter this time is put in across your component that you want to measure the voltage across. So if you wanted to measure the voltage across the first lamp there, you'd put a voltmeter in parallel, or the second lamp, you put a voltmeter in parallel, or if it was the battery, you could put a voltmeter in parallel with it. And that's how we measure voltage, using a voltmeter. Now, whenever you do voltage in series circuits, whenever you do the experiment voltage in series circuits, you'll find that whatever your battery voltage is, we'll say it's 12 volts, you'll find that your voltage or your potential difference is split across the two components, or whatever number of components are in your circuit, and they add up to give you the total voltage of the battery. So if we have 6 volts here, then obviously there must be 6 volts here as well. If I put a couple of different numbers in here, if those two, this means that these two bulbs here are equal to each other, they have the same resistance. But if you had something, and I'll change this, we'll say this one here has got more resistance and it requires more voltage, and we'll say it needs 8 volts to pass the current along. Then 12 took away 8, this one must have 4. So this one requires more voltage. This one here requires more voltage. It means it has more resistance. So 8 plus 4 gives you 12. So in a series circuit, the voltages add up. We'll call it V1 and V2. So that's the voltage of the battery. So the voltage of the battery is equal to V1 plus V2. That's the voltage of the battery there. Okay. In a parallel circuit, however, we find that that's actually different. So I'll just zoom out a wee bit so that you can see. Alright, so in a parallel circuit it's actually different. Now, if you think about potential difference, if you think about gravitational potential difference, if you had water in a reservoir at the top of a hill, like that, well, no matter how the water gets down the hill, it has the same gravitational potential energy as any other water at the top of that hill. So if you had 1, 2, say even 3 streams coming down, this is very, very like voltages in parallel. They're all starting off with the same potential difference. The water, it doesn't matter how they get down the hill, they've all started off at the same gravitational potential difference. So it's the same here in parallel. It doesn't matter how many branches you have, every single branch gets the same voltage as the battery. So there's your battery voltage, V1 and V2. So if that battery voltage is 12 volts, and V1 is also 12 volts, V2 is also 12 volts, and so on. How much current flows through each one, however, depends on its resistance. So you know the current comes from the battery and splits up, but the voltage in each branch stays the same. So even if you had a line there with 2 bulbs in it, that whole line has still got 12 volts. Now, it then splits up across each little bit because that little bit's in series with itself. But in a parallel circuit, the voltage of the battery is equal to each branch. And that's the way we would write that. Okay, so just to summarise all that, current and voltage in series and parallel. If you have a series circuit, we'll just go in a wee bit there. If you have a series circuit, then the current is exactly the same. So we'll just say the total current, I will just call it I, is equal to anywhere in that circuit that you might measure. So if you had a circuit where you were measuring current, then the current's the same everywhere. In a parallel circuit, however, the total current I splits up in each branch, and they should add together to give you, and so on, to give you the total current. For voltage, then it's the opposite. So we'll write this in red just to make sure that you see the difference. The voltage in a series circuit, the voltage of the battery is equal to the voltages across each component added up. And then it's the opposite then for parallel. Every voltage is the same for each branch, equals V1 equals V2, and so on. Okay, so there are two opposite things going on there, and if you can try and get that into your head, that's always going to be a really, really big help to you. And we're just going to finish with a couple of questions. Right, if a current of 6 amps is to run through a device for 6 seconds, what charge is delivered to the device? So if you want to pause the tape and work this out yourself before we put in the answer. So just go ahead and pause it if you like. Okay, this is the answer now. We've got a current. We've got a time. And we're looking for charge. So our equation Q is equal to I times T. And I is 6, T is 6, and that gives you 36 coulombs is your answer. So you can see there they tried to trick you. They've got amps and coulombs, but of course we want 36 coulombs is your correct answer there. Question. If 6 coulombs of charge is delivered at a potential difference of 5 volts, how much energy is delivered? So what have we got? We've got Q is 6 coulombs, V is 5 volts. We're looking for E. So we know E is equal to QV. So Q is 6, V is 5, and that gives you 30, and because it's energy, it's measured in joules. And so your answer there is 30 joules.